All right. Yeah, thanks, Jimmy and Harpreet, for the invite. I'm happy to be back once again to talk about a recent CVPR paper of ours. So this was work I had done during my internship last summer. It's called Active Data Curation Effectively Distills Multimodal Models. And yeah, as I said, this was work done during my internship with some amazing hosts, both at Google in Zurich as well as DeepMind in London. So I'll try to zoom out first a little bit and talk about what the high level goal here is. So the high level goal is we want small deployable foundation models, right? Like all the big tech companies building these large models are amazing. But the problem is if you want these models to be deployed efficiently on your edge devices, those large scale chunky models cannot really do the trick, right? Because they have large interest costs as well as memory requirements. So they're not able to run efficiently on your phones or laptops. And people have been thinking about this for a long time, right? Because getting big things to run on a small edge device is not a solved problem, but it has been getting attacked at from different solution pieces for the last 20 years or so. One key sort of strategy people always talk about here is model compression. So you have a very large model and you want to compress it into a much smaller one that then you can essentially deploy on your edge device. And when you look at the sort of solution classes under the model compression sort of space, people usually think about knowledge distillation, quantization, and model pruning. There might be many more, but these are the sort of rough, broad classes of solutions people usually try to tackle. And briefly, knowledge distillation just essentially means you have a very large model that you want to try to distill its knowledge into a much smaller model that's then going to be deployed. The idea essentially being that the larger model can act as a teacher, and the smaller model that you want to distill into is the student model. Um, in quantization, the goal is kind of different. You essentially have this large model, but you just want to try and deploy the large model itself, but at a lower precision, right? So if you train your model at floating point 32, you maybe want to deploy at a much lower floating point precision than 32. So for example, maybe FP8 or something like that. All right, sorry, 1 second. I am slightly getting confused with all the tabs here. Okay, yeah, back to model pruning. In model pruning, it's kind of similar to the quantization piece where you still have this large model and you want to then prune out parameters from the big model. And all of these pieces have been explored independently as well as been combined. And our work that I'm going to present now is also adding to this piece of the literature. So in our work, we are mainly going to be focusing on knowledge distillation. However, as I'll talk about maybe very briefly at the end, our sort of algorithm should also be complementary both to quantization and pruning. Okay, so given that background of what we are trying to do, the goal and the scope of our work is with respect to contrastive VLMs. So our research question is, how do we pre-train small-scale inference-efficient contrastive VLMs? What does that mean? Our setting is under the CLIP and SIGLIP model classes. So these are just standard contrastive VLMs that you would train to sort of match image text pairs that you source from the internet. And then we source a bunch of pre-training data sets that are primarily used in vision language pre-training, both Webly, which is Google internal, as well as Datacomp, which is publicly released. And then our image and text encoders are just standard transformers. So for the image ones, we use vision transformers, and for text, we just use a standard transformer that would operate over text sequences. And finally, we focus on three classes of evaluation tasks: zero-shot classification, image text retrieval. Both of these are standard in the CLIP setting. And then we also essentially take our vision encoder pieces and plug them into a multimodal decoder to sort of do captioning and VQA tasks. So that's the overall setup that we're going to operate within. And then the rest of my talk is going to be about what did we actually do? How do we sort of pre-train small scale but highly efficient, inference efficient contrastive VLMs that can then be deployed. And then if you take a look at what people have been doing in this space, the first thing you'll notice by just looking at the literature is there are some extremely complex distillation strategies. So some people are looking at complex weight inheritance strategies where you sort of have multiple teachers and you try to inherit the weights of those. Extensive data augmentations is quite standard, but heavily engineered. People are trying to do multi-teacher ensemble distillation. So you have not one teacher, but like an ensemble of teachers, all of which you have to try to balance and so on. People are exploring using the larger teacher model to generate synthetic captions, etc. And finally, people are developing their own bespoke architectures rather than transformers themselves, right? So you would develop something like a MobileNet v4 or Mobile One blocks, all of which are by themselves inference efficient, and then you would sort of plop on the pre-training algorithms on top. So all of these extremely from the outside might seem very hand engineered and complex. So in our work, we try to make all of these changes down to the bare minimum. So our question was, well, we want to pre-train small efficient models. Can we do away with all of these bells and whistles? Let's just try to do the simplest thing possible. And so while thinking about the simplest thing possible, I'm going to talk about a couple of immediate baselines one would think of, right? So let's say you have a massive data set D containing image and text pairs, right? Um, so if you did simple IID training, which is what Clip and Siglip and all of these other models do, what you would generally do is from the dataset D, at each step, you would sample a batch and then train the model on a contrastive loss, right? So in Clip, you would essentially just train on a softmax contrastive loss, which tries to minimize the distances or maximize the similarities between paired image text samples while minimizing the similarity between unpaired samples. And Siglip does essentially the same thing, but instead of using a normalized softmax loss, it uses a sigmoid loss that has a pairwise unnormalization. And this is just standard, right? So this is the simplest thing you can do. You have your massive data set D, you just sample at each step some random batch, and you train the model. However, note that in the first case, you're not really using any teacher, right? You're just taking your student model and training it on the dataset D by itself. There is no real notion of distillation from another model as a teacher, right? And so let's try and introduce that piece in, right? So let's say there's another model called, let's say, a T, which is essentially a well pre-trained larger model called the teacher. And we assume we have access to this, right? So if you do have access to the teacher, what one could do is you would take exactly the same setup as simple IID training, but at each step, instead of just training on the contrastive loss, you would train a distillation loss as well, which would essentially try to sort of minimize the divergence between what the teacher at that step thinks is supposed to be the logics, as well as what the student thinks is supposed to be the logics. So I'm going to skip over the details of the exact KD loss we use, but in some sense, this is very standard. This is sort of doing a logic matching over the teacher and the student distributions. So this is essentially visualizing what I talked about in the last slide, right? So if you look at the IID baseline piece, you have this massive data set D. Let's say you subsample it to S, for example, and at each step, you would IID sample a batch, which then goes into contrastive loss, right? So the left part of this puzzle is essentially what you do for an IID baseline over and over again. In the KD piece, which is the softmax distillation, you have almost exactly the same sampling method from your data set. So you simply again IID sample, and now this batch of data is essentially fed into both a contrastive loss piece as well as a KD loss piece, where the KD loss essentially takes in the teacher as well, right? So you would essentially get logits from the teacher as well as the student in the KD piece, optimize that loss, and in the contrastive loss, you would just have the standard contrastive loss from the student. So this is the general set of baselines one would think of, right? This is what you would generally do if you were given this problem. Now, in our work, we were trying to figure out ways of differently using the teacher model rather than simply doing this logic matching. And what we essentially came up with was an algorithm to take the teacher, and instead of using it to be a teacher on the logics, we tried to use that teacher to curate data from the for the student model, right? So at each step, what we do is the following. We sample from the large dataset D a super batch, which essentially can be much larger than the actual batch of data you want to train on. So let's say at each step for clip training, you would use 32K samples for training. Instead of sampling 32K, we just sample 32K into 5, so about 160K samples, and call that our super batch. So that's step one. In step two, we use this teacher now, which we call it reference, to score the super batch, and then we basically sample the smaller 32K batch from S according to these scores, right? So let me try to decouple what I mean. So you essentially get the super batch S, you essentially take then the teacher model, and for some definition of score, you score each sample, right? So you have now 160K scores. You can then simply sort the samples based on the score and take the top K percent, etc. Right? So this is a very distilled version of what we actually do, but this is essentially what we do in step two. We simply try to prioritize samples from this super batch S to form a mini batch B, that which we will finally train on, sampled according to these scores from the teacher. And then finally, once we get this mini batch B, we can again just train on that with the contrastive loss. So note that here we do not need the logics of the teacher. All we need is some score from the teacher, right? So you simply use the contrastive loss. And the natural question is, how do you score? What is this sort of score S that I've been talking about? So in our work, we use two definitions of scoring. There can be many more that we haven't explored, but we found that these two seem to be a reasonable way to score these super batch samples. So the first way is what we called easy reference. So in this, the score that we give to each sample is essentially the negative loss that the teacher model gets on that particular sample. So here theta ref essentially refers to the weights of the teacher, right? And if you try and deconstruct this, what this essentially means is that you're trying to sort of give higher scores to samples that the teacher thinks are easy or has low loss on, right? Because your score will be high when the loss is low on the particular sample, and hence this essentially means that you want to take all of the samples that the teacher thinks is easy. Hence, we call easy reference or easy teacher. And the second way of scoring is called learnability scoring. So in learnability scoring, what we simply do is instead of only relying on the teacher's predictions of of how easy or difficult a sample is, we also give the current student model a chance to do the scoring, right? Because remember, at each step you are training only the student. So the student is also getting better and better across steps. Hence, what you would like is you also want the student to be able to make some decisions on how easy or difficult each of the samples are scored. And hence, in this learnability scoring, what we do is we simply take the loss of the sample under the student model and subtract the loss under the teacher. What this is essentially doing is that it's prioritizing samples that are easy for the reference or the teacher and hard for the student model, right? So again, note that these scoring methods have been explored in prior literature under different settings. But these scoring methods essentially seem to be working very well under our contrastive pre-training setting, as I will show in the results in a few slides. However, this is essentially the bulk of the scoring methods that we use for the sampling of the mini batch from the super batch. And a nice theoretical tidbit in our paper is that we essentially show that this active curation with easy reference is theoretically equivalent to doing knowledge distillation on IID samples. I'm going to skip the theory because we don't have too much time. But essentially, you can find these in the paper if you're interested, where we show that if you use easy reference scoring with a teacher, it's theoretically equivalent to doing knowledge distillation on just IID samples. And if you did curation with learnability scoring, it's again theoretically equivalent to doing knowledge distillation on hard samples based on student. So essentially, with this slide, what I'm basically trying to unpack is two things. What our actual method is, how do we actually use the teacher to score samples? And two is just trying to sort of show the equivalence between knowledge distillation and how our curation method can be theoretically viewed as a distillation procedure. And one thing, if you notice from the last slide, is that I mentioned in step 3, you only use the contrastive loss, right? What this means is that the previous method was only an implicit form of knowledge distillation because the teacher is only being utilized for sort of giving you good samples to train on, but you're not really matching the sort of logic distribution of the teacher itself, right? To account for this, we simply combine our previous method with an explicit distillation objective, right? So the only difference from the previous slide is that you do everything exactly the same, except that at the end, you don't only use a contrastive loss, but you also use a distillation loss. And as we will show in our experiment, this improves function matching of the teacher to the student, hence giving us better performance. And in this slide, I'm basically showing you what I talked about in the previous 2 slides, right? So I direct your attention to the leftmost piece in this diagram, which is the active curation method that I first talked about. Here, S is the super batch that you would sample uniformly from the large dataset D at each step, right? And note that this coloring of samples from blue to red is sort of a visualization for higher scores, right? So in this case, red would be the highest scoring samples you would get, and blue would be the lowest scoring samples. And hence, when you do acid sample, you would just basically take the top K highest scored samples, which are all the red samples, right? So in the acid method, the only difference is that we basically apply the teacher in helping us to identify good data samples to curate for the mini batch that we train on, and then we apply a simple contrastive loss, right? Now, when you actually add back the distillation objective into acid, we do have 2 ways of doing that, right? So in the middle, I'm basically showing you the approach where you would sample the top scoring samples based on acid, apply the contrastive loss there, but you would also sample IID samples from the S super batch where you would apply your distillation loss, right? Because remember, if you have 2 objectives, you sort of have a choice of which data batch do you apply which objective on. So if you apply the contrastive loss on the acid sampled batch and the KD loss on the IID sampled batch, that's the method in the middle. And the method on the right is essentially, again, just doing contrastive loss and KD loss together, but on the sampled batch from acid itself, right? The reason we do this is because it's not clear a priori whether the distillation objective requires a different data distribution to train on compared to the contrastive objective, right? Because let's say you have a teacher which sort of is trained on a much wider data distribution, you would want the student to match the teacher's logics on a much wider data distribution, which you will not get from acid sampling, which you would only get from IID sampling. I'll talk about this a bit more in the experiments, but that's the sort of intuition for why we have these two different acid methods, which is where we combine the KD loss with the contrastive loss. All right, having talked about the method, I'm now going to talk about the results that we get, and I'm going to go through this in a structured manner where we first look at acid, then we look at the explicit version of that, which we call aced, and then finally to the scaled up version of how do we actually pre-train inference efficient models with our algorithm. So here, what we are trying to do is essentially look at the scaling behavior, right? So as you increase your sort of teacher model size or the reference model size for a fixed student, are you improving performance or not, was the question we were answering here. And so here, if I try and deconstruct the plot, the dotted lines are the IID baselines for each of the sort of different models, right? So the green color essentially shows you a tiny student, so that has 17 million parameters. The red one has 57 million parameters, and the blue one has 203 million parameters. These are the students that we train. However, for each student, we sweep across different teacher sizes, which is what is there on the x-axis. And then we basically look at performance across a bunch of classification and retrieval tasks on the y-axis. What you immediately see from here is that for different students, the optimal teacher size varies. So the optimal teacher size I've marked here in different stars. So for the tiny student, which is in the green colored line, you see that the teacher with 200 million parameters is the optimal one, after which you sort of start saturating. For the small student, which has 57 million parameters, the optimal teacher is of size 650 million parameters. And finally, for the base model, which has 200 million parameters, the best teacher you can use is essentially the largest one. So in some sense, you can kind of see this very clean scaling behavior where if you're given a particular student size, you know that you don't need to use too large a teacher to get optimal gains, which is a very nice result because using a larger teacher effectively means that you use more compute for training. On the right-hand side, essentially, we take our best acid configuration that we swept on from the left side of the plot and essentially try to figure out how much better are we doing than just softmax knowledge distillation, which is our baseline, if you remember. So on the blue line, we are basically plotting the same student model across different teacher sizes for using knowledge distillation. And in the red lines, we are essentially using our method, which is H-acid and I-acid. H-acid is the one that uses learnability scoring as the scoring method, and I-acid is the one that uses easy reference scoring. And immediately from the plot, you first of all see that our methods comprehensively beat the distillation baseline across all scales. What is also interesting is that our method with a very, very small teacher also improves over the IID baseline, which is in the dotted line. However, for a distillation baseline, if you use a very small teacher, you severely underperform compared to the IID baseline. So our method not only allows you to beat distillation, but it also allows you to actually scale down the size of your teacher and still get gains. And if you note here, our best sort of acid with the smallest teacher is still better than a distillation baseline that uses a very, very large teacher. That's this star point here. This is again showing you that our acid method is much stronger than sort of standard softmax distillation that you would do. And then we essentially try to look at how well does acid actually perform across distillation against distillation across a bunch of settings. So in this plot on the left, we basically sweep over different data sets for training the teacher and the reference, and we see that across both the data sets we swept, our acid method beats knowledge distillation. Similarly, we tried different KD method configurations. So until now, I've been talking about softmax distillation, but Many other methods have been proposed in the literature where you can use sigmoid distillation, feature matching distillation, or you sort of combine both objectives and create a distillation method that uses two distillation objectives. And across all of those objectives, our acid method with just this simple data selection is able to beat all of the KD methods. Also, we finally look at sweeping the student model size. So as you have larger student models, is acid still comprehensively beating KD? And we do see that while the gains seem to decrease somewhat, we still comprehensively beat KD even across different student model sizes. And then now I'm going to talk about how we combine acid and KD, where you basically want to take the contrastive loss on the curated batch and then add the KD objective on top, right? So that's the method which we call ACE, which is actively curating with explicit distillation. The motivation for this is very simple. If you actually do a comparison between acid and KD across all of the data sets that we explored, we do see that while on average, on most data sets, our acid method improves over KD, there are a few data sets that KD actually does improve over. And that's what I'm showing you on the x-axis here, which is the score difference, right? And this is essentially because while you do this active data curation, you might actually be sort of making the tail of the distribution worse. So you don't actually sample from the tails of the distribution because you are filtering into a very narrow, actively curated data distribution. And hence, KD might just be improving on those particular tailed evaluation data sets. And hence, the motivation is simple to just add back the KD into the piece. And then we ran a bunch of ablations where we sort of figured out that the best way to do ACE, which is the active curation with explicit distillation objectives, is to actually do both contrastive as well as distillation losses on the sort of curated batch using the teacher. Because it basically improves over the IID distill version, which I talked about a few slides earlier. And both of these comprehensively beat the IID baseline. And also when you just look independently, whether our ACE method beats both acid and KD independently, it does so by quite a big margin. And then given our final ACE method that we sort of figured out is optimal from the previous slide, we tried to train inference-efficient and Pareto optimal models on this inference compute versus performance frontier. The previous state of the art here was mobile flip from Apple, and we essentially sort of took the same training budget and simply used ACE as our training algorithm instead of the mobile flip methods. And we clearly see that we break through the Pareto frontier, and our models are Pareto optimal across this sort of performance versus inference compute frontier. We do this across 3 different sizes, F0, F1, and F2. And essentially, this large table is just to show that on most of the tasks people care about, including ImageNet classification, COCO and Flickr retrieval, as well as on average across 27 different tasks, our methods beat the current state of the art quite comprehensively. And finally, as I talked about before, we try to see if the vision encoders that we pre-train using our method can actually be plugged into multimodal models that are able to do captioning and VQA. And we actually compare this with previous state-of-the-art vision encoders with like SIGLIP and Silk. And we see that for a lower inference time image flops budget, our methods are much, much better on captioning and VQA tasks. And that almost brings me to the end of my talk. And I want to leave you with a few key takeaways from the sort of barrage of insights I've given you over the last 20 minutes. The first key insight is that if you want small inference efficient models, always looking at data is a very, very extremely effective way to distill large models. So it can even outperform sort of the current notion of KD as the state-of-the-art methods for doing this. And hence, I would really recommend, if you are thinking of doing distillation, look at active data curation as a strong way to do that. And obviously, the second thing is you don't want these to be orthogonal to each other, because we show in our experiment that even if you do data curation, plopping on the knowledge distillation piece is going to give you complementary benefits. And finally, yeah, we just showed that our models with this recipe are state-of-the-art flop efficient contrastive VLMs currently. And yeah. And there are a few exciting directions that I think I want to leave you guys with as food for thought. Because currently one thing I mentioned about ACID doing this sort of narrow data distribution curation is that it might be failing on some of the tailed concepts, right? So one exciting direction is how can we improve the current data curation method to improve tail performance by being more equitable across concepts. Another interesting direction here to explore is that currently we've only used knowledge distillation as a way to do model compression. Can our method be combined with pruning or quantization is something that is interesting to explore. And finally, all of our methods currently that we've talked about are for training inference-efficient models, but there is no reason for you not to flip the setting and you have the student be the teacher for training very large scale VLMs efficiently. And that would be the end of my talk. Thank you so much for listening. And yeah, you can find the QR code for the paper here. Happy to answer any and all questions.
Fantastic. So we will include all of the links from the talk in the follow-up email in case you missed any of them. I don't see any questions in the Q&A box, but if any questions do come in, we'll make sure to forward those along. So thank you very much for the presentation.
Thank you so much. I do see one question, I think, from Marshall, which is, did you open source a functioning VLM for independent edge inference evaluation? Unfortunately, we did not open source our models yet, but we are planning to open source the reference models that we trained for doing data curation. So I think you can reproduce all of our results because we train on Datacom 1B, which is open source, by simply using our reference model. And yeah.